So we've got 3 reactions left. We are going to have an oxidation of a single bond to a double bond. Then we're going to hydrate across that double bond. And finally, an oxidation of that alcohol to a ketone. All of that's going to leave us with oxaloacetate. And in that previous video, remember we start with oxaloacetate, adding acetyl-CoA to go to citrate. These 3 reactions are set separately because you're actually going to see them again in fatty acid breakdown and synthesis, as well as amino acid breakdown and synthesis. For us, that'll only be for those of you guys going on to Biochem 2, but that's just so you guys know that these reactions actually happen again in other pathways. So the fact that these 3 reactions tie back into metabolism of fatty acids as well as amino acid metabolism is really important. So what is now our 6th reaction, but the first in this last set of 3, is taking succinate to fumarate with succinate dehydrogenase. Since it is a dehydrogenase, we're going to expect some redox chemistry. So this is going to oxidize succinate to fumarate, therefore reducing FAD to FADH2. Now notice that we're only going to FADH2 here. We're not actually going all the way to NADH. That's because there's not enough energy in this reaction to be able to reduce NADH. We'll be talking more about the energetics of redox reactions later. Succinate dehydrogenase is actually an enzyme that's in the electron transport chain. So you're actually going to see this one again when we talk about the electron transport chain. And this one's actually then membrane bound. These electrons are going to go straight from FAD to ubiquinone in the electron transport pathway. So the FAD is bound to the enzyme, and it's going to pass things down a chain to ubiquinone. So again, the FAD is covalently bound to succinate dehydrogenase. So there's our attachment via a histidine residue. So this is that reminder. So your FAD, you do need riboflavin, which is vitamin B2, required for the synthesis of both FMN and FAD. We'll be taking a look at FMN later. Another reminder with FAD and FADH2 is that this compound goes through multiple oxidation states. So since FAD and FADH2 have actually 3 different oxidation states, they can be involved in both 1 electron and 2 electron transfers. So this ability makes them really useful in a lot of biochemical reactions because they can accept electrons easier and participate in lower energy reactions or higher energy reactions. Succinate dehydrogenase actually has 3 different iron-sulfur clusters, and they're shown here. The differences here, you'll notice, are all ratios. So whether you have 2 irons and 2 sulfurs, 3 irons and 4 sulfurs, 4 irons and 4 sulfurs. All of your irons are coordinated with cysteine residues, so that remains the same no matter what. The clusters only participate in 1 electron redox reactions, so they can only really go from that iron plus 2 to iron plus 3. And since your succinate dehydrogenase is again bound to the inner membrane of the mitochondria, those electrons are going to enter the electron transport chain and then contribute to ATP synthesis. This is shown here so that you can actually see how this all works. So what you have in here is both the FAD cluster, which is in multiple colors in the very middle of the enzyme, and then those gray and yellow parts are your iron-sulfur clusters. What happens is these electrons are essentially passed from the substrate to FAD to the various iron-sulfur clusters, and they have to be close enough, physically close enough, to pass electrons. So they're essentially acting like a wire does in the walls of your house to carry electricity. So they are still carrying electrons, which is technically electricity. It's just a very, very small amount. So these multiple redox centers basically constitute an electron wire as they can pass electrons to each other and get them out of the enzyme. We've been talking a little bit about iron-sulfur clusters. Realize that this can also go wrong. So Friedreich's ataxia is an inherited disorder that causes progressive damage to the nervous system, gait disturbance, speech problems, and heart disease, and that's because of a mutation in a gene encoding frataxin. This participates in the assembly and maintenance of iron-sulfur clusters and mitochondrial enzymes, especially aconitase. So if the iron-sulfur cluster in aconitase is unstable and sensitive to loss of iron, you get a variety of different issues because you've got then issues with the TCA cycle. It's going to cause a variety of different problems. Reaction 7, fumarase. This is going to take the fumarate that we just made and turn it into malate. So this is going to go ahead and hydrate across that double bond. This is going to be the transhydration of fumarate to form L-malate specifically. So you do get hydration occurring across this newly formed double bond, and you get this transition of water across the double bond. The actual mechanism is not known for certain, but we're going to take a look at the 2 main possibilities. So in here, the main difference in these mechanisms when we look at them is which thing happens first. So both of them are going to involve a hydroxyl group. Both of them are going to involve a proton from the enzyme. So they have that in common. The question is what happens first? So in the carbonium ion mechanism, you have first that the substrate abstracts a proton from the enzyme, leaving you a positive charge on your carbon, which then is open to the attack by the hydroxyl group, adding that hydroxyl group to give you L-malate. In the carbanion mechanism, you have the hydroxyl group attacking first, then leaving a negative charge on the carbon more easily to abstract a proton from the enzyme. So notice that again, both of them have the hydroxyl group, both of them have that proton from the enzyme. So both of them have the notion of where these atoms are coming from, but the real question is which one comes first, and we just don't know. Last reaction, malate dehydrogenase. We're going to take our L-malate and oxidize that to oxaloacid. In doing so, we are going to form, again, NADH. So this is an NAD plus dependent oxidation. The carbon that gets oxidized is the same one that just received the hydroxyl group in the previous reaction, so no rest for the weary in this case. This is actually a fairly expensive reaction. This has a fairly positive delta G associated with it, and it's basically dragged across by the next reaction. And so remember that this is a cycle, so even though we're like, oh, it's the last reaction in the cycle, it's a cycle. So oxaloacetate then will react with acetyl-CoA to form citrate. That reaction, if you'll go back and look, is highly exergonic. So this reaction being endergonic is connected to the next reaction in the chain. It also helps that in the mitochondrial matrix, oxaloacetates have got a fairly low concentration, which also helps drag this reaction forward.